Hello, my name is Alan Profit and this is road bend classification using optical flow and deep learning supervised by Dr. Terence Morley. ADAS systems are popular in modern cars. They use an array of sensors and cameras to understand its environment and then evaluate risk to either intervene or alert the driver. A subset of ADAS systems is road bend prediction. This involves detecting the upcoming bend, evaluating the risks of that upcoming bend, and then alerting the driver as appropriate. There have been numerous studies showing the benefits of a system like this. In this study, firefighters navigated complex scenes with and without the system installed, and they found that in the simulated environment, this system significantly reduced the risk of rollover. Another study conducted this in the real world, where they use high-quality GPS and maps to determine the upcoming bend and then alert the driver of an advisory speed. So for the system proposed in this report, we want to take it a step further. We want to look at vision-only systems that can detect the direction and severity of a bend from a far distance, but also we want to make sure it could handle real-world scenarios. The approach we've taken is to try and mimic human-like judgment. It was found that humans were affected by the flow of the image. This is the movement of features in a scene, and by speeding up and slowing them down, the humans understeered and oversteered, suggesting a correlation between the steepness of a bend and motion flow. Taking this a step further, it was also found that humans focus on the road vanishing point, which is the furthest point you can see along the line since it's the most informative part of the road for the bend. From this research, our report explores three hypotheses. First of all, can you use RGB sequences to classify the bend direction and severity? We're also going to look into the effectiveness of human-like motion fields as an input to the deep neural network. Finally, I want to compare if selecting the road vanishing point improves the performance of the classification model. So to explore these goals, this report suggests a processing pipeline. We broke it down into 4 key milestones. The first milestone is prepare data. This takes the raw dashcam footage and extracts the bends and their labels. The next milestone is to find the road vanishing point. And then both milestone 1 and 2 go into milestone 3, which is generating the data set. And then once you have the data set generated, milestone 4 is training our deep learning models and then evaluating their performance. So milestone 1 is prepare data. Between myself and my family, we have collected 6 hours 45 minutes of UK road footage. And one important disclaimer is we have removed night videos, so these are only day scenes. All this footage was captured using a stereo camera setup, and we are going to be taking the 4K driver's side camera as our main camera. Embedded within the video, we receive comprehensive records of the position data, the location of the car, speed, time, and more. With this information, we can move on to automatic bend labeling. We aim to detect the bends in the videos and label them with the severity and speed on the bend. We also go into output the frame at different set distances before the bend. To measure the change in heading, we have developed a distance-based approach. This involves plotting a line of best fit 10 meters before and after the current position we are analysing, and then finding out the angle between them. This is suitable for handling the noise of GPS, where as you can see with the brown counters, it doesn't always fit the path. And on the sharp part of the bend, we'll have a larger angle. The reason why I put it on a chessboard is because we converted it to the British National Grid, which is a metre scale representation of the UK. Here's some examples of it in action. You can see that it selected the start and ends of different bends, and having a look at the colour scale, it has selected the most significant bends of the scene. But just running through the examples, you can see that it has also detected some junctions and roundabouts, and we've not been able to separate these from bends. So what comes out of the system is the average speed and angle for every bend, but also the frame at a set distance before the bend. Overall, we received high accuracy and consistent labelling, but a big drawback is not being able to filter the roundabouts and junctions, and it is still quite sensitive to noise. So moving on to milestone 2, finding the road vanishing point. Quickly run through some challenges we're about to face. Ego motion is split into 2 components, the translational ego motion and the rotational. Translational is when the car changes position, rotational is when it changes heading. Collision is where we can't see part of the scene because it's been blocked by another object. And finally, we would like to handle unstructured roads, which are roads that don't have the regular landmarks such as road paint, signs, curbs. For road vantage point estimation, we want to find the end of the road. The first proposed solution is based on the fact that focus expansion has features expanding from it. As you can see here, by tracking the displacement in the x and y axis, we can get a good approximation for the road vanishing point, being where these plots cross zero. However, this system is highly sensitive to ego motion, particularly rotational. This is since turning left and right shifts the whole graph uniformly up and down, skewing the data. Solution 1 offered good speeds and a good approximation, but it was not robust enough for real-world application. Our second solution explores tracking features over a number of frames using sparse optical flow. And finally, we use the ransack algorithm to estimate where all these lines are pointing to. This approach was a lot more robust to ego motion. And as you can notice here, we have also decided to mask out cars using YOLO. This means that we aren't tracking features of moving objects. For these optimizations, we had the highest ability, but it was hard to find global parameters that worked with every video, and the computational cost of this is very high. Despite this, this is the solution that is implemented in the pipeline. Moving on to milestone 3, dataset generation. So far we have our bends and estimated RVPs, and then this goes into our generation script to generate 4 new input variants, being RGB optical flow both at wide and narrow angles. As mentioned before, this is very computationally expensive. Originally it would take just under 21 days to generate this dataset, but after some optimization we managed to get it down to 40.5 hours. And as a result we have the 4 variants. Here we demonstrate the wide view at the top and narrow view at the bottom, with RGB on the left and optical flow on the right. And with these samples we are ready for the neural network. We're going to train one model for every input variant and compare and evaluate the models using predefined evaluation metrics. Each model is trained on the same architecture. And just to give a summary, we use 2+1D convolution neural networks which capture spatial and temporal patterns within the data. CNNs are good at extracting abstract feature maps, and this allows us to get complex patterns and then dense it into a final class prediction. Quickly explain what 2+1D convolution means. You can use a 3D kernel, but by separating it into a 2D and 1D kernel, you get a good approximation and less weights to train. So model performance. We split our dataset into training, validation and test. Our samples loaded in and rebalanced, being 7 classes for the wide view and 4 classes for the narrow view. We only generated samples of moderate and sharp bends for the narrow view due to hardware limitations. Overall, the wide view models perform better, particularly the RGB model performing the best at 73.78%. The narrow view models didn't really generalize, however the optical flow model generalized better than the RGB model. So tying back to our original hypothesis, for hypothesis 1 the short answer is yes, we had generated a model that achieved 73.78% accuracy using the samples we have given it. This suggests good generalization, however more data will be required to make the system more robust. Hypothesis 2 requires further development. The wide optical flow showed good generalization, especially between left, straight and right bends. The confusion came in when it tried to detect the severity of the bend. However, overall, RGB outperformed optical flow. Finally, for hypothesis 3, we observed that optical flow generalized better than the narrow view RGB. However, both these models had a high confusion and poor generalization. This can be due to the RVP estimation, since error is propagated through our pipeline. So limitations of our system. Computational cost means that we can't have real-time performance. Ego motion presents extra challenges, occlusion of road features, and also our dataset is polluted with junctions and roundabouts. We've been able to reduce noise, however it is still susceptible to high noise. And finally, the most significant limitation the system faces is error propagation. This is where the error and limitations of individual components get carried through the system and amplified. To summarise the achievements of this system, we created an end-to-end pipeline going from the raw dashcam footage to the trained models, produced an open source dataset with 4 different input variants, and encountered real-world challenges when developing the solution. We've either discussed it or tried a countermeasure. Future work could involve incorporating additional sensors to reduce noise, utilising the stereo vision footage, and exploring more advanced deep neural network architectures. I've left the raw footage datasets and code all publicly available for reproducibility and future research. Thank you, and I appreciate your time.